Hello. We've completed our work with Euler circuits and now we are ready to go on to a different kind of circuit, Hamilton circuits. Our study of Euler circuits began with the Königsberg problem when we were trying to walk across all of the bridges without recrossing any of them. This time the problem we will start with is the traveling salesperson problem. Here we have a map of all the places our salesperson needs to go, along with the current one-way fares between the cities. Can we find the absolute cheapest way to do this trip? The places that the salesperson needs to reach are the vertices, and the flights between them are the edges. So notice that in this case, every pair of vertices has an edge between them. Now with Euler circuits, we wanted to be able to trace every edge once and only once, but we didn't care about how many times we went through any of the vertices. Now with Hamilton circuits, we are still allowed only to trace an edge one time, but now we don't care about tracing all of them. This time we only want to be able to reach the vertex once and only once. Now for Hamilton circuit problems, we're going to look at a different kind of graph, and that's a complete graph. Complete graphs are where every pair of vertices is connected by exactly one edge. So let's take some examples of complete graphs. Here's a graph with 3 vertices and 3 edges, and it's complete because all 3 of them are connected to each other. Here is a complete graph with 4 vertices. In this case, we're going to end up with 6 edges. Notice that the 2 edges that go through the center of the graph do cross, but that is not a vertex, and I cannot change my direction there. Here is a complete graph with 5 vertices, and now we're actually up to 10 edges. And finally, we have a complete graph with 6 vertices, and we end up with 15 edges. Now, complete graphs always have Hamilton circuits. Again, back when we were looking at Euler circuits, our big question was there a circuit or wasn't there? With a complete graph, we're always going to have Hamilton circuits, and in fact, we're going to have more Hamilton circuits than we know what to do with. The question for us is going to be, which is the best Hamilton circuit? So to get started, we're going to try writing out all of the possible circuits for each of the following examples. So here's our example of a complete graph with 3 vertices. Notice that I can do A to B to C to A, but I can also do A to C to B to A. Now, as far as we're concerned, those are 2 different circuits because I'm going different directions. So notice that a circuit and its mirror are always different circuits. But on the other hand, please remember, we mentioned this back in Euler circuits. I'm going to say it again. Just because I start at a different vertex does not make it a different circuit. So for instance, let's take our circuit ABCA. If I were to start that circuit at B instead and have BCAB, I'm still going in the same direction, covering the vertices basically in the same order. It's the same circuit. For this reason, when I'm trying to write out all the circuits, I'm going to always make sure that I start and stop at the same vertex. I don't care which one I pick, I'm just going to pick one to do all my circuits starting and stopping at, so that I don't duplicate any circuits by accident. So here's another example. Here we have 4 vertices. When we have 4 vertices, we're going to end up with 6 circuits. So again, I'm starting and stopping all of these with A so that I don't inadvertently double up. So I get to 5 vertices, and now I have 24 circuits. So if we look at these last 3 examples and pull the information we've talked about so far together, what conclusions can we get? Well, we had 3 vertices, and those 3 vertices, the complete graph had 3 edges. And then we had 2 circuits. For the graph with 4 vertices, we have 6 edges and 6 circuits. For the graph with 5 vertices, we had 10 edges and 24 circuits. So if I have n vertices, can I find a way to find the number of edges and the number of circuits? Well, yes, we can. For the number of edges, the formula is going to be n times n minus 1 over 2. Let's take an example. Take 5. 5 times 1 less is 4. 5 times 4 gives me 20. 20 divided by 2 gives me 10. So there are 10 edges. For the number of circuits, we get n minus 1 exclamation point. Or, in the case of 5, 4 exclamation point. Well, this is a new function, and it's a very different function than what you've necessarily seen before. The functions we've had before, like x squared, square roots, those have formulas, and I can evaluate it for anything that I want to. But this function is called a factorial, and it's defined recursively. And recursive means that to know the next value, I have to know the immediately previous one. In other words, to know 4 factorial, I have to know what 3 factorial was. So let's look at the definition. Well, to start with, the domain for the function, or the set of numbers I'm allowed to use in this function, is the set of whole numbers. That means I can't use any decimals, I can't use any negatives. It's going to be defined in terms of kind of a list of rules. So we're going to start with 0 factorial, and 0 factorial is 1. That may seem a little odd, but we use factorials in probability. So there's a reason in probability why it turns out to be 1. 1 factorial is also 1. 2 factorial is 2 times 1, which gives me 2. 3 factorial is 3 times 2 times 1, or 6. Now notice, 3 factorial has 3 times what we really had as 2 factorial, 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Well, again, remember, the 3 times 2 times 1, that's 3 factorial. So 4 factorial is really 4 times 3 factorial. Notice this is what I meant when I said that to know 4 factorial, I have to know 3 factorial. That gives me 4 times 6 gives me 24, so 4 factorial is 24. Let's try it one more time. For 5, I could multiply 5 times 4 times 3 times 2 times 1, or in other words, multiply 5 times 4 factorial. Well, 5 times 24 gives me 120. So here's our rule. Anytime I want n factorial, I'm going to take n times the immediate number in front of it, factorial. So for example, if I wanted 100 factorial, I would need 100 times 99 factorial. So let's go back to complete graphs. Here we have a complete graph with 6 vertices. So how many edges does it have? Well, it's going to be 6 times 5, that's going to be 30, divided by 2 gives me 15. So we have 15 edges. How many Hamilton circuits does it have? Well, it's 6 minus 1, 5 factorial, and 5 factorial we found earlier was 120. So we have 120 circuits. I don't think we're going to be doing this one. Here's a problem from your book. Your book uses the notation K sub 15 to stand for a complete graph with 15 vertices. So how many edges with a complete graph with 15 vertices have? Well, it's going to be 15 times 14 divided by 2. And that gives me 105. Then, how many circuits will it have? Well, that's going to be 15 minus 1, 14. 14 factorial. 14 factorial is 87,178,291,200 circuits. Well, let's think. Suppose you're a whiz at writing out circuits, and you can write out 20 in a minute. How long would it take you to write out all of the circuits for a 15 vertex complete graph? Well, if I take the 87 billion, etc., and divide by 20, I end up with 4,358,914,560 minutes. I take the minutes and divide by 60, and I will get 72,648,576 hours. Take the hours and divide by 24. That gets me 3,027,024 days. And finally, if I take that and divide by 365 for the number of days in a year, we end up with roughly 8,293 years. So, this concludes our presentation. Your MyLabs Plus Homework 5 covers the material from this presentation. Quiz 3 is also going to have questions about it. And remember, you do need 90% or better on Homework 5 before you're going to be allowed to take the quiz. Thank you very much, and I'll see you in class.